Today we're going to talk about local maximums and minimums of functions in R3, which is of course something that we'd spent a lot of time on in Calc 1, but of course when we move into R3, everything gets more complicated. All right, so here I've got graphed a function in GeoGebra z equals sine x plus sine y, and we're going to try to find spots that we would consider to be local maximums and local minimums. All right, so I'm going to turn on point A. Point A is going to be what we would think of as a local maximum. No matter which way I look at this graph, that point A seems to be sitting on top of a little hill. So in its own neighborhood, it's the biggest z coordinate around. So that will be what we'll call a local maximum of a function in R3. Point B is going to be kind of the opposite, hanging down below. That's the lowest z coordinate that you're going to find in its neighborhood. And no matter which way I turn this, it looks like it's a minimum z coordinate. Right? So those are our straightforward points. But of course, when we're in R3, something more complicated happens. We get something like point C. So when I turn this one on, point C, when I look straight on the y-axis, this looks like it's a local minimum spot, right? It's kind of a low z coordinate. But then if I turn this to look towards the x-axis, C kind of appears to be a local maximum spot, right? So it's kind of both at the same time. It's a local maximum in one direction and a local minimum in the other direction. So that point C is what we're going to call a saddle point. Kind of looks like a horse's saddle. Before we go on to talk about how to find local maxes and mins in R3, I want to review how we did it in R2 in Calc 1. All right, so here I've got just a simple cubic function, and we want to look for our local maximums and local minimums. So they're easy to spot just by looking. Here is my local minimum, my lowest y coordinate in the neighborhood, and then my local max is over here, my biggest y coordinate just in that neighborhood. And we would figure out where these were by looking at the function by thinking about the tangent line. So when I turn on the tangent line, when I'm at that local max, the tangent line has gone completely horizontal. So y prime is equal to 0. So we would take the derivative and we'd set it equal to 0, and it would just sort of find all of the spots across the function where I would have that 0 slope or that horizontal tangent line. And we would call those numbers for this function that's 1 and 2 point something along the x-axis. We would call those critical numbers of the function, places where the derivative is equal to 0. And then we had to figure out a way to tell, is this a local minimum or is it a local maximum without cheating and looking at Desmos? So probably what you did was you made a sign chart, right? You would find out that the derivative had you decreasing and then increasing and then decreasing, and then you could tell whether you were at a local min or a local max. That is called the first derivative test. And it's one way to find if you have a local minimum or a local maximum at a given critical point. The second way you may or may not have learned, it's called the second derivative test. I'm going to turn off this tangent line. And I'm sitting here at this minimum spot here, but if I didn't know it was a minimum and I just knew that the critical number was 1, I could take the second derivative of the function and plug in x equals 1. And if I did that, I would get y double prime is equal to 4. And remember what the second derivative tells you about the graph of a function. It tells you whether the function is concave up, like a cup, or concave down, like a frown. And so because my second derivative at this point is positive, it means the function there is concave up. It looks like a cup at that point. And if you're concave up, the only possibility at a critical point is that you're sitting at a minimum. If I go over to my other point, my maximum here, the second derivative is negative there. So if you're sitting at a critical point and you know that you have a local minimum or maximum, but you're concave down, your second derivative is negative, you must have a local maximum. That's the only thing that could be happening. So this is how we're going to think about things in R3. We're going to kind of do a very souped up second derivatives test to figure out if our critical points are local minimums, local maximums, or those weird saddle points. All right, so we're going to talk about our souped up second derivatives test when we get together in class, but in the videos today, we're just going to talk about those critical points. So remember in R2, we just took the derivative and set it equal to 0. In R3, we've got two derivatives to think about, the derivative with respect to x and the derivative with respect to y. We're going to set both of them equal to 0. So to have found a local min or a max or a saddle point, you need that both of those derivatives are equal to 0, not just one or the other. Okay, so that's going to be our critical points. The majority of them are going to be just where both partials are equal to 0. It's also possible to find critical points where one of the two of them are undefined or where both of them are undefined. This would be kind of the R3 version of a cusp or a corner, some sort of sharp corner on the graph. But by and large, most of the ones we're going to do are going to fall into that first category where the critical point happens when the first order partials are both equal to 0. So we'll do a couple of examples of finding critical points in the next video.